I think Dr. Sanjeev, we can begin if you're ready.
Yes, ma'am. Yes,
Ah,
ma'am. Yes.
all right. Dear students, today we have Dr. Sanjeev who's going to talk about automation in serology. Dr. Sanjeev is a professor of microbiology at Lady Harding Medical College, as you can see from his first slide, and he's also a dear friend. This is again the second part of our series on automation. First one was bacteriology, this is serology, and the next one is going to be molecular diagnostics. So, over to you, Sanjeev, for an engaging session, and I'm sure more
Thank
people
you.
will join in as we move.
Okay, ma'am. Thank you so much, ma'am. And I uh, welcome all and thank you so much, ma'am, for giving me the opportunity. I hope I'll be able to do justice. This is one very important topic. As you know, we all are seeing this serological test that is in the diagnostic field for last many decades. But there is a need of automation that already you have seen in the class of bacteriology, why it is important. So let's see why this serological test needs automation. So the layout of my talk will be overview of the conventional and methods a little bit. We'll not go into the depth, but because I believe that you know about the ELISA and the different methods, and just we'll discuss about the limitations of why we require the serology automation. Then go for a little bit of fundamental principles related to automation, then advanced immunoassay technologies. There are many in the field of automation in the serology, but I'm picking up the important ones which actually are using in a diagnostic and most of the areas. And little bit we touch on emerging advanced technologies. So this is a class actually basically kind of a more of a what do you call the discussion on the pen paper, but in a it's kind of a didactic mode and online. I hope I'll be able to make you understand a little bit of what do you call the mechanisms and other things. So conventional method, you all know we have tests like precipitation, agglutination, neutralization, confluent fixation, Western blot, ELISA, and immunofluorescence. They have their own, the advantages and disadvantages. But the ELISA and immunofluorescence, these are the two techniques that we worked a lot, and these are the two techniques that have a lot of scope for automation. And we have done a lot of automations of these two principles, if I say, and making a lot of automated platforms for high throughput testing in a laboratory. Uh, we'll see one by one why it is required. So if you see, like just to give you an overview of the ELISA, we have ELISA starting from the direct ELISA to competitive. So the direct ELISA one is a very simple form where you have a capture antibody, then your antigen, and where an enzyme level antibody, where is a conjugate antibody, will come, get attached, and you put the substrate, and this enzyme substrate complex breakdown give a color reaction. So that is a basic funda of ELISA that we all know. Then you go and make it bit complex to make it more specific and sensitive, like the indirect ELISA where you have two antibodies you're using, secondary antibody without labeling. Then you have secondary antibody with a conjugated antibody with an enzyme. Then you're using the substrate. So you want to increase the sensitivity level. The sandwich is like you're making the two bread pieces are your capture antibody, which is coated on the plate, microtator plate, and you have the antigen, and you have a detection antibody, conjugate antibody with an enzyme. When you add a substrate, you break down and you give a color. So these things are there with their advantages and disadvantages. So we want to utilize this particular technique only to automate the entire system. Why? Because when you see the ELISA, see the complexity, starting from the pipettes, how you're doing. Like I say, if you say it will require a lot of skill, both the physical as well as the mental. And as we know, we make sometimes a lot of error in this. So okay, somebody says increase the volume. Uh, one second. Am I audible now? I believe I'm
Yes,
audible.
yes, 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 yes. Now you're audible.
Yeah. Okay. So here, like a lot of the physical and the mental processes they come in the picture. कि आप जैसे हम पिपेटिंग कर रहे हैं, you need a lot of skills. There can be a lot of errors in terms of how much volume you're doing, what is your pipeting technique, how you're making the dilutions, which require a lot of practice. So there are chances of error starting from how you're doing it. Later on, how you're doing the calculations, because mathematical dilutions in a calculation we do mostly, manually. There's always a chance that you make mistake. So there are a lot of scopes for improvement. That is the need of automation. So other the problems that you have said, if you divide in the conventional problem, there are problem with sensitivity and specificity. You must have seen in the practical, a scenario that different kids, their sensitivity will vary from, the 30% maybe to some kids are good to 100% specificity. So that's a problem. That means reproducibility is a problem. Again, is a dependent performance. मतलब हम late stage में कोई diagnose कर रहे हैं, early stage में जैसे HIV. So window period में हम diagnose नहीं कर पा रहे. So we need tests that you can detect the particular antigen or antibody specific to that particular disease that you can diagnose early. Cross reactivity is a big problem where you want to increase because they're non-specific binding with a similar looking antigen or antibody. That is a problem with the conventional assays. Another thing is the interpretation challenge. As I told, it is the mathematical calculation of dilution, then calculation of the OD value with the PC and NC that you have seen with all those calculations. And in certain assays, like the radioamine assay, there is a problem with the hazardous substance. And quantification. In certain serological tests, you know that quantification is essential. And most of the ELISA technique conventionally, we have mostly the qualitative ones we are doing. So reproducibility as a test because there's a batch-wise variability. Even we see for a particular assay, like as for example, I'm going to do the hepatitis B surface antigen detection. If you see, there may be variability in the batch, or there may be variability in the sensitivity and the specificity in two different kit manufacturers. They depend what kind of antigens, what recombinant antigen, how much purified antigen they are using. So validation is also limited. What are the kits that are available in the market? Changing serological profile because in the entire process of the disease that the profile changes, the what are the markers and other things, so you need a very sensitive and specific assay. Also the problem is that in a high prevalent population, like as for example a particular disease is prevalent, so if your kit is not validated properly or not sensitive or specific, it will give false positive result. So in a way, it can underdiagnose or it can overdiagnose by giving a false negative result or false positive result. So taking these challenges or these limitations, we have the scope for automation. So if you simplify the automation fundamental principles, it starts from sample processing to reporting. Like in the sample processing, as you see, if you can do the barcoding, so first thing first, the pre-analytical में ही आपका mistake नहीं होगा. So if you do the barcoding and with a robotic precision using those technology, so it will limit your manual errors. Like जो हम note करते हैं, so वहाँ पे बहुत सारे mistakes होते हैं, transcription error can be there. So this is one part of the automation technique in a sample processing, cutting, sorting, as well as reagent addition. So if you see most of the machines nowadays, the reagents are added in a kind of a what do you call a small robot. Like they every time they will dispense the quantity in microliter which is required. So essay execution, ultimately, there is a software installed in the system which is validated, robust validation with doing aqueous. So that with time precision है कितना time incubate करना है, कितनी बार washing करना है, reason कितना dispense करना है, controlled by the software, so it becomes more precise. Signal detection by optical, like light कोई generate कर रहा है, कोई fluorescent generate कर रहा है. So we have machines detect those fluorescence or light by we'll see in the later part of my lecture that things called photomultiply tubes or different cameras so that the amount that is there in an analyte can be precisely measured. Data analysis, automatic algorithm, because you do not have to do the calculations manually. Your software going to do algorithms are there. AI and machine learning tools are also integrated in automation. So you need to remember one thing: AI is a different thing, and the automation. Automation is a rule based. Like I'm telling you, iska, this is the work I want you to do. If I add a machine learning, that means I'm giving some brain to it. That like some instruments, they can detect a hemolysis sample. I'll see like OBAS and other things where chemiluminescence has say they can, if you put the hemolysis sample, they will discard. So these machine learning techniques, if you give along with the automation, to again your precisions and of your test is increasing. Reporting, as you all know, you can integrate these systems with your lab information system. That is a very, very good thing, so that the clinicians can access at the real time, or you can so that they can take a decision at the right time, for what you call the diagnostic utility of your test will also increase. So these are the fundamental principles, starting from sample processing to reporting, taking in consideration what was the challenges in a conventional serological technique. So now advanced immunological techniques kya kya hai hamare? I'm going a little fast because it's a bit long, so want to complete it. Uh, like we have alpha, as you know, enzymatic fluorescence assay, then clear, then everybody is talking about the chemiluminescence immunoassay. The other is that E-clear electrochemiluminescence assay, then chemiluminescent microparticle assay, and multiplex bead-based immunoassay. So more or less, if you see, they all are based on some kind of a chemical reaction or a electrochemical reaction and the luminescent principle. So we go one by one. We have different platforms using these different principles. Now, one thing I'd like to mention here. So, as I have mentioned in the earlier slide, that we have different ELISA technique, like sandwich ELISA and competitive ELISA. So, this particular machines, if I name like a machines, where this automation is happening, they will use one of the principles of ELISA. Also, like they will सैंडविच से एंटीजन सैंडविच का मतलब क्या होगा दो एंटीबॉडी के बीच में एंटीजन लेके उसके बाद का जो केमिस्ट्री होगा that chemistry can be chemiluminescent, that can be fluorescent. So that is the basic principle you need to remember. So what is fluorescence? As we all know from the class, what you call the earlier knowledge, that this is a particular atom with a nucleus, तो हमारे electrons घूम रहे हैं. When you put a light on that, so it will put one electron to the higher energy state. Energy state में क्या होगा electron is quite unstable, so the electron wants to come back to the normal the stage. So doing this, they will lose energy. While losing energy, they will lose gradually. So एक part आएगा जहाँ पे energy loss करेगा, तो in terms of some light it will emit, so that we call fluorescence. So interesting चीज है यहाँ पे, whatever that light we are giving to excite, that we will call the excitation light, and whatever we are getting is a emittent light, emission light. So दोनों में एनर्जी का डिफरेंस है. दोनों में अगर एनर्जी का डिफरेंस है, दैट मीन्स वेवलेंथ में भी डिफरेंस है. दैट इज व्हाई we'll see later part how it is utilized. So this is the basic principle of fluorescence. So fluorescence ऐसे जब हम detect करते हैं, like there is a light source, then you have multiple spectrum of light, we have excitation filter, we want like this green light to come and excite the sample, which is tagged with the fluorescent level. So this is we'll call, that excitation light. And whatever is getting emitted is different. The color is different, the wavelength is different, and these two are vertical to each other. Where you see in ELISA, it was more of a ELISA what? A colorimetry, the color detection. But a monochromatic light is going passing through the lens and the sample, and it is giving a color of a same wavelength. तो यहाँ पे क्या हो रहा है? Excitation and the emission, जो light है दोनों की energy अलग है, wavelength अलग है. So based on this, this is actually a variation. Enzyme ring fluorescence is a variation of ELISA where we are using a fluorogenic substrate. So if you see here, so antigen antibody complex. Here I'm giving a conjugate antibody and substrate is added. Depends on what kind of substrate you're adding. It's a chromogenic substrate. It will give color. If it is a fluorogenic substance, it will give fluorescence. So that is why we call it a variation of ELISA, which is alpha. So fluorescence and chromosome. Color change and there is a fluorescence. Okay? So it is widely used for detection of either antigen or antibody in your sample. We use one term called analyte. Analyte means कुछ भी हो सकता है. Antigen detect करना है कि आपको antibody detect करना है. So basic step in my slides, you will see I'm writing a lot of things so that later on you can read. So that is why I find my slides will be busy, but I will not suggest you whenever do a presentation, don't make the slides so busy. So in this thing, first we do a coating. Coating क्या होगा? आपका antigen या antibody coating होगा, right? In your well, microtiter well or whatever the आप microtiter well ही मैं बोलूंगा यहाँ पे, instrument के हिसाब से अलग होगा. Then you block the sites so that non-specific binding now. Non-specific binding से क्या होता है? in this whole enzyme link thing, there will be a lot of noise will be there. So we want to block the noise. So the basic aim of this automated technique in serology is कि हम background noise को कम करें ताकि हम specific binding करें एंटीजन और एंटीबॉडी का. सैंपल एडिशन करते हैं. सैंपल एडिशन में इधर एंटीजन होगा, एंटीबॉडी होगा. Then what will happen is a capture antibody which is there in a microtubule plate. Antigen you have given, then on top of it you have given an enzyme level antibody. Same principle going on. So the enzyme will be sandwiched. That is why I'm saying they are utilizing the principle of sandwich alike. Then on wash, हम wash क्यों करते हैं? Multiple washing करते हैं ताकि unbound component जो भी रह जाता है well से हमको हटाना चाहते हैं. So did you get specific binding between an antigen of or antibody of a interest? Then we add a substance here, fluorogenic substance हम add करेंगे. As I told you, then I'll do a reading with the excitation light giving energy and I'm getting the emitting energy in a different wavelength, and I'll get a fluorescent intensity which will be measured in a spectrophlorometer, and the signal is proportional to the amount of target is present in the sample. So in a way we are doing a specific binding, and we can do a quantification also. So again, I'm saying difference in a tabular format, detection, color change in ELISA, fluorescence in alpha, substrate यहाँ पे हम क्या देते हैं? Normal substrate, TMB हम देते हैं tetramethylbenzidine or p-nitrophenyl phosphate in ELISA. Here, this name is important for methyl ambidiferyl phosphate. This is a fluorogenic substrate. रीडिंग यहाँ पे एब्जॉर्बेंस कर रहे हैं हम स्पेक्ट्रोमीटर फोटोमीटर में, हमें यहाँ पे फ्लोरोमीटर में फ्लोरेसेंस रीड कर रहे हैं. सेंसिटिविटी दोनों का कंपेरेबल है. स्टडी शोज अल्फा इन सर्टेन assays the sensitivity is higher, and we'll see the other advantages when it comes to the instrument. Incubation time is very important. Here in alpha, the incubation time is lesser compared to the other ELISA technique. Background noise, as I have told, background noise is less and depends on what kind of a plate you're using. But depending on a different machine is different. But our main target, as I told you, we want to have a specific, the reaction between the antigen and antibody. So we want to decrease the background noise. So one such instrument that you all must have seen in your laboratory is a Vidas. So here again, I'm saying I'll name multiple machines here, but nowhere I'm promoting them. But these are the common machines that are using, the platforms that are using in our serology laboratories. So this principle alpha is used in Vidas. One was the mini Vidas, and this is Vidas. We call mini Vidas. There are two such cassettes. Here it has increased to 3.5. So in this 5, again you have wells, or you can say you have put 6. So 6 5 is 30 if you have the winners. So in this we can put different tests. We'll see. So this one is a principle of alpha. So layout, as I told you, यहाँ पे 5 है कैसेट, यहाँ पे आपके 1 2 3 4 5 6 wells है, जहाँ पे आपके strips जाएंगे और भी ऊपर एक कुछ जाएगा. We'll see what is that. So there, the components, if you see, they have the controls, the calibrators, and other diluents are there. These are the strips, and these are, जो मैंने यहाँ पे दिखाया था, this we call the SPR. We'll see what is SPR. So everything is bar-coded here. These are the components. तो जो स्ट्रिप है, स्ट्रिप में क्या है, आपके सारे डाइल्वेंट है, कंजुगेट है, और लास्ट में जाके सबस्ट्रेट है. And these are bar coded. When you have the bar coded, you can actually trace back, and it becomes easier for you to load in the machine. And one portion that is covered, one you pierce it and you put the sample in one place. So here we put the sample, and diluents are there, wash buffers are there, and then last point here is a substrate. Now, this is it acts as a pipette, because जैसे हमने बोला कि solid phase को हम coat करके रखते हैं. So this SPR, that is solid phase receptacle in Vidas, is coated with either antigen or antibody and acts as a pipetting device. Strips में हमारे जो required diluent है, buffer है, conjugate है, substrate, everything will be there. Just you have to put the reagent strip. So for one patient, one specific result. So strip will contain the 10 wells containing all the diluents and the buffers that is required for the test. And it is bar coded. where everything is level from the essay code to lot number to expiry date. So आपने सैंपल लिया, आपने एक स्ट्रिप पे लोड किया, एसपीसी यहाँ डाला एंड स्विच इट ऑफ. यू सी इन द वीडियो. सो सॉलिड फेज रिसेप्टिकल में क्या हो रहा है रिएक्शन? डाइल्यूएन में सेकेंडरी एंटीबॉडी होगा जैसे एलाइजा नॉर्मल विथ एन एंजाइम दैट इज कॉन्जुगेट. क्या रहेगा यहाँ पे? एएलपी. सबस्ट्रेट मैंने क्या बताया था? 4 methyl अम्बिलिफेरल फॉस्फेट विल बी द लास्ट वन. एल्कालाइन फॉस्फेटेस के साथ सेकेंडरी एंटीबॉडी आया. सो ये पिपेटिंग डिवाइस के जैसे काम करेगा तो मल्टीपल टाइम्स इट विल गो अप एंड डाउन. So it will do buffering and the washing, everything will happen inside. So there is a sandwich reaction. Two antibodies are used. And telling again and again this thing. First antibody at the reaction tube, secondary antibody conjugate with alkaline phosphatase, and the substrate is 4-methyl amyliphenol phosphate. So, end of this reaction, diluent, washing, addition of conjugate, finally the substrate when is found is see the 370 nanometer the excitation filter and the 450 nanometer there is the detection of light from 4-umbelliphenol sulfate, which is detected in the photomultiplier tube. So this is again I'm saying the two different wavelength, two different energy. So if you see in a schematic diagram, so all this that these are the coated in SPC, these are the coated antibodies, then antigens are coming. If it is sample, you want to detect antigens. Then the conjugate is there, enzyme conjugate will get attached, then we are touching the substrate. And on the substrate is fluorescence, 4-umbelliferol sulfate. So you're putting light, excitation light, emission light, and getting the light and detecting the fluorescence. So two reactions are happening here. One till conjugate immunological reaction. After the addition of the enzyme substrate complex, it is the enzymatic reaction. So why advantage क्या है? It is automated. आपको जितने भी pipetting है, dilution, washing, everything is happening inside. Output हम किस में measure करते हैं is important. RFV, relative fluorescence value, or qualitative, based on the threshold value, depending on the assay you are doing. So it is 100 times more sensitive than ELISA. There are different studies have shown for different analyte it is different. सिंगल टेस्ट फॉर्मेट उसका मतलब क्या हुआ? आपको एक टेस्ट लगाना है तो यू कैन पुट वन टेस्ट ओवर हियर. विल सी इन द वीडियो. यहाँ पे हम एक टेस्ट स्ट्रिप लगा सकते हैं फॉर लाइक आई एम टू डू हेपेटाइटिस बी. But in this particular cassette, I have to put one type of test only. You cannot mix. Okay. And these SPCs correspond to this particular strip. सो एक टेस्ट लगाना इमरजेंसी में एलाइजा में हमें बैच टेस्ट करना पड़ता है. तो एडवांटेज है सिंगल टेस्ट फॉर्मेट, थ्रूपुट आप ये टाइम बहुत कम लगता है. स्टार्टिंग फ्रॉम 35 minutes to 1 hour is the maximum. So the high throughput can results you can get. Reproducibility, the coefficient of variation is 3 to 9%. Good results, reproducible because everything is barcoded, everything is measured inside. मिनिमल हैंड्स ऑन टाइम. आपको बस एसपीसी आपको स्ट्रिप में सैंपल लोड करना है एंड एसपीसी लोड करना आगे एंड मशीन ऑन कर देना. सो दिस इज अ इंटरफेस. I want to show you just when I'm putting a hepatitis B surface antigen or what I'm putting here. Uh, yeah, hepatitis C. I'm putting a hepatitis C and I'm putting a sample ID. Whatever. Then we create. This is the interface. So यहाँ पे आ गया कि strip 1 में आपका first rail में आपको ये डालना है. So here and we take the strip, load it here. Already sample has been added here, and then put the SPC corresponding to that particular strip for ACV. बस हो गया and you run it. And नीचे आपका आ जाएगा कितना टाइम आपको लगेगा. So the another test we are putting here, like here, C मैंने दिखाया. Now here I'm putting another test, like I'm putting a say hepatitis B. मैं क्यों दिखा रहा हूँ आपको बताऊंगा. यहाँ पे वहां पे आप लोगों ने देखा था एक सैंपल हमने डाला था और वहां पे एक ही वेल में एक ही स्ट्रिप डालने के लिए बोला था. Like the sample. Here I'm putting hepatitis B, putting the sample ID, and I create. So one thing you see, I'll stop it here because here it is see एक sample आपने दिया था लेकिन 4 चीजें आ गई. Standards and control. That is a one thing because in ELISA every time we have to put the controls, positive control, calibrators, and a negative control. Here, like if I have put run a control और स्टैंडर्ड्स आर नथिंग बट द स्टैंडर्ड सैंपल जिनकी आपकी वैल्यूज पता है, जो एक स्टैंडर्ड कर्व देगा, एंड योर एनालाइट ऑफ इंटरेस्ट विल कंपेयर whatever the graph we are getting, compare the standard curve and give you the result. So standard आपको बार बार रन नहीं करना है. Like here in hepatitis C standards नहीं आया क्योंकि वो हमने एक बार लगाया था, मान लो that standard of the control will be valid for 1 month. But in hepatitis B आपको remember भी नहीं करना है. Once you put the sample, automatically ले लिया कि हाँ आपका expiry हो गया control, so you're putting the controls again. That means by doing this automated technique, so you don't have to put the controls again and again. You will not forget, and every control and the standards will have a validation every time. Automatically it will take. ठीक है. So C का ये था और B का आपने देखा कि चार आगे दो स्टैंडर्ड्स हैं दो कंट्रोल. And the running time will be like different. किसी का half an hour, किसी का 45 minutes. So इस यहाँ पे E के लिए because standards and controls है there, तो reference values आ गए, भी आ गए. C के लिए हमारा एक है, controls ये नहीं दिखाएगा क्योंकि इसमें controls valid. So this is how we get the results, and this is about this Vidas with alpha. So advantage, standard protocol, fully automated, optimized reagent handling is a closed system, efficient washing and blocking. आपको इसमें manual काम नहीं है तो errors भी नहीं आए. Now performance of the Vidas in the different studies, they have shown very good results for the different analyte like ACV. Some are 100%, 99.5% sensitivity and specificity compared to PCR and other immunoassay. I'm just giving one or two examples. RSV detection also with the DFA got an agreement of 92%. So various, tests are there. What do you call? Okay, please do speak in English. Hindi. I'm so sorry. I'm so sorry. Okay. Uh, um, so here the RSV detection, I'm giving an example for that. So if you see, there is a lot of studies going on with the alpha principle, and it shows a very good results in compared to the other established techniques on automation or other techniques. So these are the the test available. What do you call the menu for the Vedas? You can see from the emergency, like the Procal is one very important thing. To cardiology, to thyroid profile for us very important. The hepatitis B profiles, so that is important. Uh, Okay, somebody say Hindi mix is really helpful anyways. Okay, so infectious disease profile like hepatitis. Hepatitis profile is very important. HIV, some people are doing because, depends on what kind of a laboratory you're using, but we are using mostly the hepatitis and the torch and results are very good and comparable. So the allergy testing, tumor marker, reproduction fertility, because FSA stage, and HCG you can detect. So it is very good if one sample is coming in emergency, like, if I say like Procal, so you don't have to wait for the batch, right? In ELISA, you have to wait for the, like some samples to put because every time you cannot put the controls. So here, single test we can put in the emergency, it works really good. So next is we are coming to alpha हमारा खत्म हुआ. Alpha is now we are coming to luminescence. So we are coming to chemiluminescence. So let's see what is luminescence. It's like nothing but the radiation that is emitted by molecular atom when these species are returned to the ground state. More or less simple, the same chemistry. So it can be photoluminescence, chemiluminescence, and bioluminescence, depending on what source of energy you're giving. Photo, when the excitation energy is tribes of light. Chemi means the energy for the excitation is coming from some kind of chemical reaction. Bioluminescence, that means some biologically catalyzed reactions providing the energy. So here, chemiluminescence already, here the chemiluminescence, that means there is a chemical reaction which is providing an energy to excite the, electron for the particular analyte. And when it comes back to the normal state, light is released and emission of photons. Photons are a particle of light which you are going to detect on a photoemitter multiplied tube. So the chemical reactions, if you see that they actually generate a sufficient amount of energy, push that electron to a higher state. When it comes back again and again, I'm saying because this is the simple chemistry which is working everywhere, detection is different. So detection of the photon is photomultiplied. So now chemiluminescence immunoassay. Now clear means chemi. There is a chemical reaction going on. Luminescence, that means detection of light. Immunoassay, that means the chemical reaction is nothing but the reaction between the antigen and the antibody, where there is our interest, whatever we have to detect, antigen or antibody. So the name says a chemical reaction, light detection, and immunological reaction. Why it is important? That sensitive. It is very, very sensitive. The sensitivity goes up to 10 to the power minus 18 for the attomolar. So now all the assays they're trying to make their assays of the automation so that you can detect a very low level of analyte, starting from the femtogram level like 10 to the power minus 15 to japtomolar concentration at 10 to the power minus 21. So your assay, whether an assay or the platform is good, that depends on what is the lower limit of detection. So this assay, chemiluminescence assay, has around 10 to the power minus 18 moles of detection. Specific binding of antigen antibody, easy for automation, no radiation hazard like any, radioimmunoassay. And the best part is that there are different reagents. The shelf life of the reagents is long, which is a very good thing. So that you can store it for a longer duration of time. Waste is less. So immunoassay, there is a core is the part is the specific binding of an antigen and corresponding antibody. Sample will be same again. The target analyte can be antigen antibody. Again, a secondary antibody or antigen is coming. Same like ELISA, but here it is level with the chemiluminescent molecule. That chemiluminescent molecule हो सकता है, or it can be attached to an enzyme like horse peroxidase or alkaline phosphatase. So if you see here, so I'm putting this ELISA just to give a reminder how they captured antibody and we have a detection antibody making a sandwich of the antigen. Here, like here in the solid phase, I have immobilized my capture antibodies, putting the analytes. Analyte will come, the epitope and a paratope will combine together. Now I'm putting a secondary antibody with a biotin conjugate. Biotin will act as a ligand for attachment to the detector antibody. So iodine level, it will again, antigen will be sandwiched between this conjugate and the capture antibody. Now I'm using a streptavidin. Streptavidin is nothing but a tetramer protein where you have, tetrameric that can bind to the four other antibodies. So this complex will come, there will be binding of avidin conjugated with what? Conjugated antibodies enzyme, it will be enzyme conjugated. Now here the substrate will be chemiluminescent substrate like luminol or other things will come to it. When you add the luminol, then there will be again the whole chemistry will occur, excitation, emission, and the light will be generated, which will be going to detect. And we'll measure it in the relative light unit wave. So this occurs very fast. So basic principle is same, but only detects on what kind of substrate you're using at the end. So the chemiluminescent, that means the chemiluminescent labeling is a core component of CLIA. So there can be two categories. One is the direct chemiluminescent labels, which are like luminol, luminophores we call, or enzyme based. That enzyme has to act on it, then only you can give a luminescence. So the chemiluminescent labels, like direct and indirect. Indirect means through enzymes, alkaline phosphatase or phosphatase peroxidase. Now, direct chemical levels are actinium ester or ruthenium complexes. A very good, the directly they act in the presence of some alkaline environment. And when it gets oxidized by some agents like hydrogen peroxide, they will go excite to some intermediate. They form some excited states and some intermediates will form. When they come back to their normal state, with a lot of electron exchange and other chemistry, so they will release the light, they release the energy, and the rapid flash of light, generally at the 420 nanometer within seconds. So this is how a direct chemiluminescence assay is working in alkaline environment in presence of hydrogen peroxide. So this is good because it doesn't require any secondary antibody additional substrate and it is highly sensitive and simple. We will see it has been used in other assays also. So this is direct and indirect are enzyme based. So horse peroxidase or alkaline phosphatase. Like For horseradish peroxidase, we'll use one chemiluminescent substrate, luminol, it will act on luminol. Or for alkaline phosphatase, we'll use one substrate called AMPPD. So these enzymes will catalyze this substrate conversion to the excited states. That means they cannot go to the excited state directly. They need this enzyme to, take them to the excited state. When they come back, then again release the light. So the luminol, the enzyme will be activated by hydrogen peroxide. There will be oxidation of luminol to luminol diazequinone. Then a lot of intermediates will form. Then again come back to the relative state, resting stage, and release light. It can be enhanced by additives like idophenol compounds. And then in the alkaline phosphatase system, what it will catalyze the dephosphorylation of AMPPD, resulting in light emission. So the substrate is getting activated by these two enzyme system. In the direct, the rutinol there, in presence of hydrogen peroxide, they're directly they're getting into excited state. So this is the chemistry, a lot of intermediate forms are formed coming back and the release of light in enzyme-based chemistry of HRP and IP. So if we compare, so you have seen the direct luminophore actinium ester. Activation method is just hydrogen peroxide. But in HRP and AP, we need the luminol and AMPPD as a substrate. These enzymes will work on that. Another directly acting luminophore is very, very, that people are working on. It's a ruthenium complex. In electrochemical activation, we'll come to it when you see the electrochemical assays. So emission wavelengths are different. Application mode are also different, depending on whether it's a direct chemiluminescent level or indirect chemiluminescent level. So signal detection, whatever light is detecting, we're detecting for photo multiplier tube. Talking about for the last couple of minutes. So what is happening here? The photon energy, what is the components of light, are getting converted to electrical signals. And because it's a very tight, the light tight chamber, so there is no background noise. So, and what we are detecting at the end of the day, RLU, that is relative lights unit. So here, there are a lot of components of photomultiplier tube, this is called PMT, where we are converting this photon energy into electrical energy in a high energy state. I'm not saying high energy state, there are a lot of, that anode, the diodes they are using, so that multiple electron passes through secondary emission each day, so that we can detect a good signal in the luminometer of photomultiplier tube. So this photocathode will convert photon to electron via photoelectric effect. So this is in short how you're detecting the light energy to converting it into a electrical signals. Signal quantification, what will be happen, the amount of light detected will be directly proportional to the concentration that is there in the target. And what is standard curve is generated? Standard curve, standard curve is a known concentration of the analyte. Then whatever RL you are getting will compare with the standards by the machine and give you a card for your analyte. And the best part is the linearity and a wide dynamic range of clear. What is linearity and wide dynamic range? That means the detection limit. The detection limit starts from where? Lower limit of detection to the upper limit of saturation. So any particular assay, your accuracy will depend on what is the limit of detection. Because if it is too much, like the upper limit of saturation, the linearity of the actual concentration of the analyte and the curve will not be maintained. And the dynamic range is a scale of this, to the limit of detection. So to make it simplified, so every assay should have a very lower limit of detection and upper limit of saturation. If you go to the upper limit, that is why if the more light is generated, the more concentration the analyte we're getting, they actually discard it. So that's how they maintain the linearity of the reaction. So types of clear format will be, again, I say it depends on the different ELISA format. So mostly you're using the sandwich clear that for the antigen detection, or it can depend on the competitive ELISA principle or direct and indirect, because the direct is not very specific. The indirect, there may be cross reaction between, because a lot of antibodies are using. The sandwich is mostly they're using this principle. So we have different machines and the platforms in the clear format. But using, you see here, the main thing over here is end of the day, the fluorescent level. We're using either a direct fluorescent level or a enzyme chemistry, either alkaline phosphatide or actinium ester. The actinium ester is getting a lot of importance nowadays because it's very, very sensitive and you know, uh, gives a good reaction and a specific reaction. So if you have to differentiate between the ELISA with this is a chemiluminescence, there is a color, specificity, they go up. As I said, the limit of dynamic range is higher. Cost, obviously, if you want to get something better, you have to pay for it. Automation, fully automated, and sample volume is an example, but it differs from different assay. So basically, the range is good, low emitter detection is also good. Advantage, again, I say high sensitivity to attomolar concentration to picomolar concentration. Sorry for this error, 10 to the power minus 18 to 10 to the power 21. Wide dynamic range, low background noise, because the background noise will come from the non-specific binding of the antigen antibody. Here, the specific binding of antigen antibody, and the noise can also come from the contamination of your reagent, from the contamination of a sample, unwanted binding of the proteins and other substances present, where they prevent it. So low background noise. And the rapid and stable signal, because the enhanced chemiluminescent reaction can provide an intense and a prolonged light emission. And this is a very good property of actinium ester. It provides an intense and a prolonged light emission. So that is why there we'll see in an electrochemical reaction, it gives a very good specificity. So where we can use it, like with us, we can use it in different clinical scenarios, starting from endocrinology, oncology, cardiology to metabolic disorder, infectious disease, not to mention about SARS-CoV-2, then you can list is numerous. They're working on it, and every time this new, what do you call it? If you know the chemistry, only thing you have to include is the specific what do you call the purified antigen or the antibody corresponding to or against that particular antigen antibody you have to detect. So that is why the list will go on. So this is very good actually, troponin TNI, because you know these are emergency markers. You cannot just wait to put an ELISA. So you can put a single test also. And sometimes a high throughput lab, they have to perform a lot of tests, maybe 1,000 tests a day. So these platforms are good in that scenario. So one system will see this is your Vitros system. In the Vitros 3600, we have this system with us. Here, the well is a microwell technology. What is the microwell technology? Everything is happening in this small well. This particular small well, like microtiter well, this is a small well we are using where the capture antibodies are coated. On that, your analyte will come and other reagents will put on that, like enzyme conjugate on the substrate and other thing. Everything is happening here. So the reaction again is an automated process. All the advantages will be there. No contamination. The reagent addition will be, precise. Precision will be good. So dynamic range is high, because of which you do not have to play with a lot of dilutions, and a TAT is also faster. The best part, because of the small this thing, extremely low analyte concentration again can be detected, and a small volumes of sample can be also detected by this particular machine. So you see, this is the one, this is the diagrammatically representation. This is the well which is coated with your capture antigen or antibody. So as it is a conical shape, because of which the surface area will increase. So that is why whatever kinetics is happening, antigen and antibody, that will be involve the patient sample and the reagent binding, that will be specific. Also, it can work in a very small volume sample. Sometimes the precise samples are coming, we cannot get a repeat sample. So this technique is very good. And there is called a swirling type of effect, because it's a conical small, there's a mixing of all the reagents with your analyte in a more, that properly it is occurring and a more active binding. Whereas the sample volume is less, reagents are using in a very, less volume. That is why we are minimizing the waste also. So here we'll see, I have shown this is the basically where the reactions are happening, that we need the reagents for the different assay. They have a reagent, and these reagent packs are properly validated, and that they have their own validity as a longer validity period. So again, the same assay, same principles are using here. So here is an example, as I have shown in the streptavidin chemistry, where enzyme to link substrate and ultimately what you are using End of the day, it is a chemiluminescent substrate you're using. So the studies have shown that the direct chemiluminescence, this vitros has got a very high luminescence they are generating, and compared to the other test, the detection limit, as I told, we can go to the the L2 molar concentration at 10 to the power 8 to 10 to the power 19. So again, here also, same thing I have shown in the clear that goes from, starting from infectious disease panel to the non-infectious to the inflammatory markers. The list will go on, and definitely in the future we'll get more and more of that. So this is one video I'd like to show where we are putting these samples over here, sample loading area. And here the small, if your volume is less, you can put it here, where you show small volume. So the processing will start from this area. Everything is happening. Tip sealing. There is a photometer lamp where the light will be generated. And there is one thing you can detect the hemolysis, AI. So you can discard it. And other samples also, finally, the samples will be discarded after the reaction is done. Then you have sample metering because they have to aspirate. From here, they will take from the sample how much reagent to be put, how much you have to aspirate. Everything is there. The tubes, aspiration tubes are there. And here, you will load. These are the tips where the reaction is. Yeah, aspiration. They act like a pipette. What I showed a reagent for that particular case, you can put a reagent load, and the best part is that for multiple tests you can run, and you can put up to like 8 to 10 reagent load over here. ऐसा नहीं है कि it's not like that you have to run one particular test type only. If you have any hepatitis B, C, you can run. So washing probes for the different washing cycles for the unbound things, and then you have this, yes, reagents, probes, and this is the incubator, and this is a luminometer for detection. And then you have these buffers here. You can store the buffers as required to washing step that we know. Discarding are also here. Sorry, we are here, right? Yeah. Buffers are there. Discarding jar is here. The waste. Ultimately, the pipetting device will come down here. This is another waste bin. When the reaction is over, they will discard everything. This is the dispenser for all those pipette, what is the receptacle, versa tips. This is everything. We put it here. From there, it will take by itself. And there is one processor over here that is this is main control unit. Everything is controlled. This thing. So this is just to show you that principle. Along with this machine, how it's working, everything is automated over here. Starting to put the sample, and the best part is the sample is very low. Also, they can detect. You just have to give the pipetting tips. They will take it. The buffering is there. They will wash it. Everything will be automated, and you can run a multiple test, and this particular machines are good for the high throughput testing. So now another one we are talking about electroluminescence assay. This is also chemiluminescence assay, but electro, that means we are giving some excitation of the electroactive molecule here by giving some electrical energy. So what is that electroactive molecule you use here? That is ruthenium based luminescent label we are using. So what will happen? We'll see the chemistry. What is ruthenium? There is a tris bipyridyl ruthenium. This is an electroactive molecule. When we use electrical energy, it will go to excited state and will come back and will give a light. So we are actually applying, everything is same. Your magnetic particles, streptavidin coating, then ruthenium level we are using, and we are applying voltage at electrode. And TP, I'll come to it, there is some co-reactant also we use. So there are two types of reaction occurring here, electrochemical and the oxidation and excitation. Electrochemical, that means the ruthenium, this will be oxidized at an electron here, at an electron to tris bipyridine ruthenium 3 when a positive potential of voltage is applied. And a co-reactant molecule like the tripropylamide is also required. Now, there will be a lot of intermediate products will form. From there, it will come back to, the normal state. When it comes to the relaxing state of tris bipyridyl tris phosphate, this ruthenium that will emit light at the wavelength of 620, 640. At the same way, we can detect the light energy in the photoluminar tube, and the amount of light is exactly proportional to the consummation analyte. Again, see, it is going up and up the entomolar range. Some studies have shown that the electrochemiluminescence can go up to the jactomolar range, that is 10 to the power minus 21. When the whole automation market of the science is playing on basis of it, to what level of lower level of entomolar or the japtomolar we can detect. So here everything is same. We are using the electrical energy and the electrode, the voltage is applying with some for the electroactive molecule that is ruthenium, tris bipyridyl ruthenium. So this is one chemistry for E-clear. And they say the E-clear, as you say, that sensitivity is better than clear. It is all because of this ruthenium complex. It has higher sensitivity, picomolar, entomolar, it is japtomolar, also automation, stable reagents like clear, oxygen tolerance. Like unlike the luminal assays, that doesn't require degassing. You don't have to take out a gas from the solvent. So it is very stable. And it works with a very, co-reactant, as I said, we require TPRA, so it can work to diverse co-reactant and versatility because it can work in a wide range of analytes. You can detect proteins, hormone, antibodies. So everything is the attribute goes to the ruthenium molecule. So you have different automated platforms depending on this CLIA. The COBAS has got different versions which works on E-CLIA principle. And also the market is ruled by the Roche Diagnostics and the Siemens. They have different platforms and the different infectious and non-infectious markers can be detected here. And routinely we're using. And that depends on which one you are purchasing or you're getting, depends on uh, definitely at the cost and how much test you want to do or your lab does. Now, applications in clinical diagnostics, starting from cardiac troponin to alpha-fetoprotein to infectious disease diagnosis, HIV, HBV, SARS-CoV. And the best part of these assays, like as I told in the beginning, that we conventional ELISA, we miss the window period. We wait for the antibodies to come here. As the concentration, the lower concentration we can detect. So in kind of HIV also, the fourth generation ELISA the e-clear principles, the machines are based on e-clear principles and detecting in a very short duration, like the P24. So this is the utility of e-clear, which is nothing but the variation of the clear with the electrical energy is used with a compound called ruthenium. Now, another one is the chemiluminescence microparticle. It will again the same. It is another subtype of clear only. We're actually using the magnetic beads mostly, but sometimes we use non-magnetic microparticles also. So here, with the wells is coated with the microparticles, then your antibody coated over here, target antigen coming, again the conjugate antibody with the HIP you are giving, and you are giving a substrate or luminol or whatever, direct or indirect, and you are getting the light. So this is chemiluminescent microparticle because you are coating this with magnetic beads. When you use the magnetic beads, the advantage is that again the specificity or the specific binding of the antigen and antibody will increase, and the stable binding will be there. So if you compare the clear may or may not use microparticles. Labels are typically acrylinium ester. And here it can be luminol or anything. Basically, we're using actinium ester, which is the direct chemiluminescent level. Separation is a magnetic separation. This is depends on assay design. Sensitivity is very high due to efficient capture and the low background noise. Automation, there are many players in this. So magnetic beads when you are using, under principles of CLIA. In simple terms, that becomes a CMIA. That is your chemiluminescence microparticle immunoassay. So there are a lot of manufacturers, starting from the architect of the different variations from the about diagnostics, small to medium throughput. It depends. Again, as I say, it depends on what is the throughput of your laboratory. And all these machines have got their own detection limits and range of detection, along with the profile, what they want to detect. But mostly they detect all the parameters of the infectious and the non-infectious panels. Now coming to, as I've completed the Alpha, then the CLIA, then the eCLIA, then the CMAI, these are the main technology platforms we are using in a different machines, like if I name like a Cobus or the Architect. So there are new technologies coming, it's called Digital ELISA. Digital ELISA is basically to detect a single molecule detection, where we want to increase the sensitivity to 10 to the power minus 15 or up to 1000. There are a lot of assays for the detection of the neurological disorder, prostate cancer markers. They're actually used for detection of the marker, particular marker, to digitalize the entire ELISA process. There are a lot of platforms today in the market. One is in a, the particle is a nanoparticle based. We can see the research mostly happening on a nanoparticle level, where you can detect a very sensitive detection of the tumor marker like CA15, CA125 when it is like in a very low level, not that you are waiting for the disease to progress. So using the nanoparticle technology, incorporating the gold nanoparticles, we are enhancing this ELISA technique to go into the picomolar concentration of detection and increasing the sensitivity. Another is a nucleus sequence-based amplification, which is linked with ELISA. That means want to combine the both RNA extraction amplification with the ELISA. It is used one or two, studies have found it's a mycovector tuberculosis RNA or some viral genotype detection like rotavirus with the improved sensitivity. So these are a bit of emerging technologies. There are many. So I'm talking in terms of like, PG in your exams and for understanding like nanoparticle based, or we are using the sequencing nucleic acid amplification along with the ELISA and also doing a digital ELISA detection of single molecule. So the summary that the automated systems, because we are decreasing the sample loading, the reagent dispensing, the incubation, everything is going in automation mode. So the error, they're reducing the error, and the results are coming in the higher sensitivity and specificity. And we can integrate this with your laboratory information systems. It's good for the clinician, good for maintaining of record in a database. And all the automated serology is a superior analytical and clinical performance compared to the manual or the rapid diagnostic test. And we will see in the future, we'll see more development on this. And these are rapid. Best part is rapid and reliable for high throughput lab. These are very good. And like we do not have to wait for the batch testing, like as we have seen in Vedas, or you can see that a single test can be performed also in a Chemi in Cobus that we can put up to 10 reagent load. You can put multiple tests, like, if you're doing torch, you can put like, the toxoplasma IgG, IgM, the rubella IgG, IgM, everything together. Otherwise, in a normal ELISA, we are putting one test today and taking hours for incubation. Here, the incubation time is also less. Also, the background noise is less, so signal to noise ratio is also decreasing. So this is all for from my side. Want to cover in 1 hour, and thank you and Jai Hind from my side.
Yeah, thank you, Sanjeev. That was very exhaustive and very comprehensive at the same time.
Thank you,
So
man.
thank you
Looking
so
forward to
much.
covering 1 hour.
Yeah, I think all of the topics are covered, especially the question for the PGs is covered. So
Yes, ma'am.
anybody has a question, can they please put it in the chat box or unmute yourself and ask? Somebody wants to ask what are the limitations of these automated systems?
Ma'am, I think if I say the limitations for us, if you say one is the terms of cost, and another is the terms of what do you call it, depending on the load of the test. Like it's not like that, it can be a white elephant for you. Like, you do not have that much of throughput of the test in the laboratory, but you're buying a machine for at a higher cost. But at the end of the day, though the reagent they have a long shelf life, but end of the day, if you're not using your inventory management will go haywire. And basically it's not useful for you. So this limitation in the sense that they are mostly useful for the high throughput labs And the cost is one of the biggest limitations in a country like India. Because in a resource limited setup, we cannot think of using this. So these are the two main limitations. Otherwise, when you compare, the automated systems, they have their own pros and cons. Like as I have told you, like CLIA and eCLIA, if you compare, if you can buy automated systems, which depends on the principle of eCLIA, that definitely give you more, that sensitive results compared to that. So you cannot call it a disadvantage, but they have their own limitations. Ma'am, can we get video recording as I missed the initial part? Ma'am will answer.
Yes, Sanjeev. Actually, what happens is that we have an IAMM PG Masterclass YouTube channel where you can
Yes, ma'am.
watch this. This was streaming live, and you can go to this YouTube channel also and watch it. Majority of our students actually watch it on the YouTube channel only, as
Yes,
per
ma'am.
when you're reading these topics and
Yes, ma'am.
going along. So just go to
Yeah.
YouTube and you will see. And we don't believe in giving you the presentations because they will just lie in your mailbox or in your computer.
Yes.
I have thousands of them lying in my computer, and you will never open them and read them. So whenever you are studying serology for your exam or serological techniques, or you're preparing for exam, just go to that YouTube channel. You will be able to hear it, make your notes, run it at your own pace at 2x, 5x, or 1x, or half x. And I think it will be more beneficial.
Yeah. Ma'am, I'd like to mention, as ma'am said, that it's a very good, initiative by taken by IIM. And as I'll repeat like this slide of mine. This is very busy. So I am making like, a lot of sentences over here so that when you go back and read, so we can understand. That's the reason I'm putting less images so that you can
Mm,
read these slides as a note. But when you're making
yes,
a presentation, kindly don't follow this. This, this is not a very
uh,
good PPT presentation, I'd say.
I
Can I
agree. I
say
agree.
something? I don't know whether you can hear me. I'm Dr. Ravinder here. I
Hi,
just
ma'am. How are
happened.
you?
I just saw
Hello,
your
ma'am.
message, so I put on. Normally, I always forget. So it was nice of you to remind. It was an excellent session to know about the latest techniques and everything.
Thank you, ma'am.
Uh,
Thank you, ma'am.
I feel happy because some of them we introduced in our labs and we are using them.
Yes,
But
ma'am.
what I feel one major limitation is, I don't know, you can correct me, that we are becoming more and more dependent and on the I mean the companies, their things, what they take out, we have to be dependent on them, their latest things, and if they change anything, we are at their mercy, and so many other things. But I guess that's what happens as you become more automated, because things are not in your hand. Everything is dependent on what is provided to you. What do you say? And they're expensive.
Yeah, definitely,
Yeah,
ma'am. This is very, very.
very
Ma'am,
valid point, ma'am. But ma'am, actually, uh, I don't know. I was only 1 year old when the 71 war happened, and after that, we've had a war where we watched everything from drawing room, or rather, our bedrooms, and we
Hmm.
watched the wars play at the press of a button in the past 15 days.
I know
So,
technology is what it is.
so we can't run away from technology. And I
Exactly,
said in my
exactly.
introductory lecture also, ma'am, in bacteriology, that one of the biggest disadvantage of having automations is that you continue to lose your skilled manpower. I have
yes,
seen it
ma'am.
in my own lab. Once multi comes, it becomes
Yes,
so difficult to teach
yes,
TSI and
yes.
Durham's tubes and all that. But I think we have to all move on with time.
Yeah, I know,
Otherwise,
I know. I
we'll be
guess so.
left
But I
behind.
only hope we can afford it and we can maintain it.
Yes, yes, yes. I
Yes, ma'am.
think Sanjeev
Yes.
was saying something. Sorry, I stopped you.
No, 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 ma'am. No, ma'am. That is what my take is. But at the same time, ma'am, what I feel like when you have this, I'll take these things are there, and this is disadvantage what you and or ma'am has discussed. I feel a certain advantage of it also in a way, ma'am, that in our laboratory recently we got this vitros 3600. So then I see my technology is also kind of trying and leading this, that I see in the video. What is a luminometer? How it is working? What are the substrate?
Hmm.
They actually going and trying to learn the new techniques also in a way,
Hmm. Right.
which is also I think the good side of these things, ma'am. Though, as you said correctly, that that sometimes you might lose it. You're not putting the normal ELISA and losing the pictures of the pipetting. But knowing about the recent advances with science is also a brighter side of it. I take it that way. But again, the limitations are there, as you have mentioned.
Yeah.
Definitely, we have to move on, and that's right.
Yeah.
Definitely. Very good. Thank you. I hope I don't know how I've missed quite a few lectures. I shouldn't have missed. You should be reminding Sonal at the last minute.
ठीक है मैम. I usually try to put it on the next day. Anyway, next Friday is Dr. Ove's lecture on molecular diagnostics. So this is a whole month devoted to automation. So thank you so much, all the students and ma'am, for joining. Thank you, Sanjeev, once again. So I'll
Thank you so much, man. Thank you for giving me the opportunity. Thank you all for
and
patiently listening. Thank you, Korma. Thank you.